Our next special variety of series is called a geometric series. A geometric series. And the form, anything in the form, a times r to the n. This is a geometric series. Now, there are some very special things that happen here. First thing, for our purposes and for our results that we will be using, that's a very key disclaimer. For our work and the results that we're going to be obtaining, when you write a geometric series, we will always assume a geometric series starts at 0. If you have the entire geometric series, we start at 0. It's a very special case. So it's important to write that every time. So n equals 0, there's no confusion. We're going from 0 to infinity. Essentially, it's not set in concrete, but essentially all the other series we'll be working with go from n equal 1 to infinity. But here we start at 0. And the form is any number times r raised to the nth power. Now let's see what we get if you expand this out. If you expand it, just to investigate what's happening. When n equals 0, r raised to the... Oh, there's a few restrictions. We must assume that r is not equal to 0. R is not equal to 0 when we're dealing with a geometric series. If r is equal to 0, then r raised to that is going to be 0, and this is 0 times a is 0. This is the constant sum at 0, and there's nothing going on. So for our purposes, whenever we're dealing with a geometric series, we will assume that r is not equal to 0. It's called r for a specific reason. You'll see it here in just a minute. Okay, so when n equals 0, any non-zero to the 0 power is equal to 1. So this is a times 1, which is just a. And that's why this value of a, this coefficient, is called the initial term, because the initial term is always just that number. When n is 1, this is a times r to the first power, which is a times r. When n is 2, this is a times r to the second power. And then a times r to the third power. Notice to go from one term to the next, you just multiply by r. And then you multiply by r. And you continue. And if you take any two terms and divide them, take any two consecutive terms, take any two consecutive terms and simplify, divide them, you get r. This is called the common ratio. And that's why the letter R is chosen to represent that. So that's not a particularly big deal for us, but there it is. So those are the terms. And it's geometric. Geometric is a larger type of entity in which each is a constant multiple of the previous. It's called a geometric progression. So that's wonderful. Now, the question is, when does a geometric series converge? Well, here's our rule. And this is not very difficult to show. In fact, the textbook goes through a very basic and very straightforward argument. I'm not going to argue that. I'm not going to present that proof in interest of time. But the text is very straightforward. Okay, a geometric series converges if and only if the absolute value of r is less than 1. The absolute value of r is less than 1. R is not 0. It could be positive, it could be negative. That's why we're doing absolute value here. But if the absolute value of r is less than 1. So let's do some specific cases here. If I have 6 times 1/3 to the n. So that's 6 times 1/3 to the n. That is a geometric series. A is 6, r is 1/3. What are some other little examples here? We have n equals 0 to infinity. Another example I have here is 3 times 5/2 to the n. Number 3, we could have 2 times 0.75 to the n. So there's nothing that requires this to be fraction. We can have decimal values. Another case we could have is I have 5 times, and I have negative 2/3 to the n. So these are all geometric series. A and R, A and R, A and R. So there's no issue. A could be negative. There's no problem with that. So the question is, do each of these series converge? Well, it's very easy. It turns out a geometric series converges if and only if the absolute value of the common ratio is less than 1. So if the question is, do they converge? Well, ignore the 6. That's irrelevant. Take R. So we would say the absolute value of 1/3 is less than 1. Yes, therefore this converges. In this case, the absolute value of 5/2 is not less than 1. It is not less than 1. Therefore, this diverges. This series does have a finite sum. This does not. Here, absolute value of 0.75 is less than 1. Yes, therefore this converges. This actually does have a finite sum. And then lastly, this is what, notice we're taking absolute value. Absolute value of negative 2/3 is equal to 2/3, which is less than 1. Ding, yes, therefore this converges. All right? So geometric is about as straightforward as it can possibly get. Just check the value of the ratio, common ratio. If its absolute value is less than 1, then it converges. If the absolute value is greater than 1, if this were negative 5/2, the absolute value is still negative 1, or is not less than 1. So take the absolute value. If it's less than 1, then yes, it converges. We have another piece of information about geometric series. If, and this is a big if it does converge, if it does converge, then the sum is equal to A over 1 minus R. And again, the textbook does a nice, neat little argument as to why that's the case. For our purposes, we will accept that as a brute fact. Is A over 1 minus R. This is minus because of the formula. If R is already negative, you take that into account when you simplify. So in each of these cases, number 1, so this does converge. If it does converge, then we can find the sum. So if it does converge, number 1, I'm just going to abbreviate instead of using the whole thing, just abbreviate here. Okay, so this is A, in our case, A is 1/3, A is 6 over 1 minus 1/3, which is 6 over 2/3. You have to do complex fraction. That's 18/2, which is 9. So this converges. The sum is equal to 9. Number 2, there is no sum. Diverges, the words series diverges means there is no sum. In the past, that's how you know a student doesn't really follow what you're saying, because they'll say the series diverges and then they'll say it is equal to something. Diverges means it isn't a number. There is no number. So number 2, there is no sum, the end. All right, let's clear this out. Number 3, this does converge, and so the sum of 2 times 0.75 to the n, that sum is given by A over 1 minus R, which A in our case is 2 over 1 minus 0.75, which is 2 over 1 minus 0.75 is 0.25. 2 divided by 0.25, I believe that works out to be 8. But don't make me swear to it, but I think the arithmetic works out to be 8. All right? And then number 3, sorry, this is number 4, isn't it? Number 4. We have the sum 5. This is negative 2/3. It did converge, and so the sum is equal to a over 1 minus r. A over, be careful, 1 minus r. 1 minus negative 2/3 is 1 plus 2/3. 1 plus 2/3, 3/3 plus 2/3 plus 3/3. 3/3 plus 2/3 is 5/3. And that works out to be 3. All right. So geometric and telescoping, if they do converge, you actually can find the sum. In general, big deal. Geometric and telescoping are the two whose sums you can find. Geometric and telescoping are the two whose sums you will be expected to find. Others, it turns out, you generally cannot find the actual value of the sum. So, for any series, the question is, does it converge? If it's geometric, if it's telescoping, and it does converge, then you will be expected to find the value of the sum.